Good day, physicists! Welcome back for another installment of Physics in 5. Today, we are going over the rules for significant figures when recording data. It's important to remember that when you are recording data, you are recording numerical information. And therefore, since we are getting these numbers from measuring tools, we must use significant figures to reflect the accuracy of our measuring tools. So here we go. When we are using instruments, there are two major categories that we can think about. We can think about digital instruments and we can think about analog instruments. And in a moment you will see examples for both of these types of instruments. But as far as the significant figure rules, how they work for recording measurements. If you have a digital instrument, what you do is, with the reading that you have, you will retain all sig figs. So basically, whatever number of digits, whatever number of significant figures the reading is on your digital display, that is the reading that you record for your data, which you will use later on. On the other hand, if you have an analog instrument, the rule is that you will estimate one significant figure beyond the smallest division that you have. And you may say, well, Mr. H, what on earth does that mean? Don't worry, because we're going to go over a couple examples, both for digital and analog instruments and recording sig figs from the readings. So here we go. All right, so here we have our first example, which is a digital instrument. This is a scale, and we're not going to worry right now about the units that go with this reading. We're just going to focus on the digits for now. So if I look at my scale, I can see that my reading is about 5.7. So let's set that aside for a moment. And we'll just make a note that, okay, our reading is 5.7. And based on the rules we've already learned for sig figs, we know that this reading has two significant figures, the 5 and the 7. Now, since this was a digital reading, that means that the actual value that I'm going to record for my data, my actual measurement, is going to be 5.7 because I'm retaining the number of significant figures I had for my reading. So since I had two sig figs on my actual display, my official measurement, what I'm actually going to put down for what I measured, is also going to be 5.7. So there's a straightforward example of how you can use sig fig rules for recording on a digital measuring tool. Next, we'll look at what will you be doing for an analog instrument. So here we have an analog instrument. The one that we're looking at here is a meter stick, and I am measuring the length of a pencil here. So I have two pictures, this one just showing the overall length of the pencil and how I'm getting my measurement. And then the second picture is the one we're going to be a little more interested in because it's a little more zoomed in. So let's take a look at this for a moment. So what we have here is the tip of the pencil, specifically the eraser end, and it lines up more or less right about there on the meter stick. And you'll note that it's lining up just slightly less than this tick mark right here, which represents 18.9. So our measurement right now is approximately 18.9, but not quite. And that's the problem with analog instruments. There's a little ambiguity, a little uncertainty in what the reading should actually be that's recorded, because we just don't know. It's not an exact number. It could be 18.8, or it could be 18.9. We just don't know. It's somewhere in between. So what you do when you have this uncertainty is we're actually going to extend our measurement by an additional significant figure. So the first thing we need to do is recognize how many significant figures do we have in our reading. Well, whether it's 18.8 or 18.9, regardless, each of those readings has 3 sig figs in it. So what we're going to do now is we're going to estimate our measurement out to 4 significant figures. And we are going to estimate what that 4th significant figure in our measurement will be. So for our actual measurement, I can already say that it's definitely going to be 18 point something. Well, it's going to be less than 9, greater than 8. So we'll put 18.8 in there. And now, what I'm going to do is, just based on what my eyes are telling me, it looks like the end of that pencil is closer to being 18.9 than 18.8. And by my estimate, it looks like it's about 8/10 of the way towards being 18.9. So I'm going to put an extra 8 at the end of my measurement. And again, this last 8 that I put in here, this is me estimating out by 1 significant figure, because I think it's about 8/10 of the way between 18.8 and 18.9. So ultimately, that leaves us with a measurement now that, instead of having 3 significant figures, has 4 significant figures. And again, this works for any analog measuring tool that we would be using. So anything that does not have a digital display on it. Okay, physicists, it's your turn now. Time for you to try out these rules for significant figures when recording measurements. So for your first test, we have a stopwatch that has recorded a time here. And I've already told you that the reading is 1.16. So it has a total of 3 significant figures. The question is, what will you be recording for your measurement? Pause now, give it a thought, and then hit play again to have the answer revealed. All right, let's see how we did. So if you said that the measurement you would be recording based on this reading is 1.16, then you are correct, because this stopwatch has a digital display. It's right there. Therefore, that means our measurement will have the same number of significant figures as the reading that we see on the display. So since we had 3 significant figures for our reading, we will have 3 significant figures for our measurement. Just like that. Okay, physicists, time to really see if we know our stuff when it comes to significant figures when recording measurements. Here's an example where we are measuring the volume of a liquid using a graduated cylinder. And as you can tell from the markings on the scale, the smallest division that we have is 1 milliliter. And we know from prior science classes that when we are looking at reading off the volume of a liquid, we must read from the meniscus, or the lowest point of the liquid in the cylinder. And our meniscus is right about there. So that's where we're reading from, that pink line that I just drew. Take a moment, think about what type of instrument this is, and therefore what rules we will be applying for our significant figures. Hit pause, give it a thought, and then hit play to come back and see how you did. So at this point, let's go over what the answer would be for what we would be recording for our measurement here. First thing is we need to understand what is our reading and what type of instrument this is. Since we don't have a display, like with the prior example, that means that this is an analog measuring tool, and therefore we will use the rules for analog measuring tools when it comes to significant figures. Now, looking at the scale, it appears that our reading is above 22, but it's below 23. So it's somewhere between 22 or 23. And knowing our rules for significant figures, that means that our reading has 2 sig figs. Now what we have to do, since this is an analog tool, we need to record our measurement as being one more significant figure. So our measurement will have 3 sig figs in it. And for that third significant figure, we're just going to estimate what it is. To me, and this is just me making my own estimation. You could have made your own estimation that's different from mine. It looks like it's about halfway between, exactly halfway between 22 and 23. So for my measurement, I put down 22.5, which again has 3 significant figures. One more sig fig than the actual reading was. And as long as for this value you had 3 significant figures where the number was something between 22 and 23, then you are A-OK. And congratulations, now you are an expert on the rules for significant figures when recording measurements and collecting data. Till next time, physicists. Till next time.